Okay, so we have a physics PhD qualifying examination practice problem number 2 in classical mechanics. Okay, so consider a particle moving in the potential V of R equals negative K over R plus alpha over R cubed, where K is greater than 0 and absolute value of alpha is much less than 1. Okay, so part A, B, C, D, E, F, G. Part A, derive the effective potential. Part B, determine the condition for circular motion. Part C, find the radius of the circular orbit. Part D, determine the frequency of small radial oscillations about the circular orbit. Part E, determine the orbital angular frequency. Part F, calculate the leading order apsidal precession per orbit. And for part G, for alpha is greater than 0 and alpha is less than 0, determine whether the periapsis advances or regresses. Okay, so this is a central force motion and orbital precession problem. We're going to assume planar motion because any central force motion is confined to a plane. So for part A, the effective potential, Lagrangian is L equals 1 half m times the quantity r dot squared plus r squared theta dot squared minus v of r. And because theta is cyclic, we could say this L equals this partial L with respect to theta dot equals m r squared theta dot happens to be conserved. Thus, theta dot is L over mr squared. Total energy is E equals 1 half m dot m r dot squared plus 1 half m r squared theta dot squared plus v of r. Going ahead and substituting theta dot equals L over mr squared. E equals 1 half m r dot squared plus L squared over 2m r squared minus k over r plus alpha over r cubed. So we could conclude from that the effective potential is L squared over 2m r squared minus k over r plus alpha over r cubed. Moving along to part B, determining the condition for circular motion, circular orbit condition. Circular orbit has constant radius here, r equals r naught, so r dot equals 0 and r double dot equals 0. So equivalently here, that dv effective dr at r equals r naught equals 0, so that dv effective dr is going to be equal to negative L squared over mr cubed plus k over r squared minus 3 alpha over r to the fourth. And we're going to have negative L squared over m r naught cubed plus k over r naught squared minus 3 alpha over r naught to the fourth equals 0. Multiplying by r naught to the fourth, we get negative L squared over m r naught plus k r naught squared minus 3 alpha equals 0. Thus, the circular orbit condition is k r naught squared minus L squared over m r naught minus 3 alpha equals 0. So that's for A and B. Moving on to letter C, find the radius of the circular orbit. Okay, so here's letter C. Whoops, sorry about that. Letter C, radius of the circular orbit. K r naught squared minus L squared over m r naught minus 3 alpha equals 0. And r naught equals L squared over m plus or minus square root of L to the fourth over m squared plus 12k alpha over 2k. So the physical positive radius solution is going to be r naught equals L squared over m plus square root of L to the fourth over m squared plus 12k alpha over 2k. Okay, so we have a Keplerian in this. For small alpha, expand around the Kepler radius here, that r sub capital K, that equals L squared over mk, and let R naught equal that R sub k plus delta R. Sorry about that, delta. Substitute into k, R naught squared minus L squared over M, R naught minus 3 alpha equals 0. Now, since L squared over M equals K R sub K, we get K times quantity R sub K, that capital K, plus delta R quantity squared, minus K R sub capital K times the quantity R sub capital K plus delta R, minus 3 alpha equals 0. And then we have K times this quantity R sub capital K squared plus 2R sub capital K, delta R plus delta R squared minus K times the quantity R squared, R sub capital K squared plus R sub capital K, delta R minus 3 alpha equals 0. So we get that KR sub capital K delta R plus that K delta R squared minus 3 alpha equals 0. And to first order an alpha, we neglect that delta R squared, that KR sub K delta R equals 3 alpha. So delta R equals 3 alpha over K R sub capital K. And so R naught, that's going to approximate R sub K plus 3 alpha. K R sub capital K equals L squared over MK plus 3M alpha over L squared. Okay, so that's for letter C. For letter D, they want us to determine the frequency of the small radial oscillations about the circular orbit. Okay, so doing that, frequency of small radial oscillations. Small radial oscillations are determined by expanding the effective potential near R naught. Okay, we're going to let R equal R naught plus rho. Absolute value of rho is much less than R naught. The radial energy given here, A equals 1/2 M R dot squared plus V sub EFF R. V sub EFF of R naught plus rho equals V sub EFF of R naught plus 1/2 V double prime, V sub EFF double prime, R of R naught, rho squared plus going on and on and on. Because V sub EFF prime of R naught equals 0. Okay, this is because this happens because of this. Sorry about that. And thus, the radial perturbation behaves like a harmonic oscillator with this omega sub R squared equals 1 over M V sub EFF double prime of R naught. Okay, so picking up with that, we have some more to go on the next page with this, getting the second derivative. So continuing with D. Okay. Whoops, a daisy. Well, not sure what's going on here. Sorry about that. Little comedy. Find the second derivative here, that V prime V sub EFF prime of R equals negative L squared over MR cubed plus K over R squared minus 3 alpha over R to the fourth. So then that V sub EFF double prime of R, that equals the following here. So omega sub R squared equals this quantity. All right, now using the circular orbit condition, we're going to get negative L squared over M R naught cubed plus K over R naught squared minus 3 alpha over R naught to the fourth equals 0. Multiplying by R naught to the fourth, we're going to get this equation. Isolating L squared over M, that equals K R naught minus 3 alpha over R naught. Substituting into V sub EFF double prime of R naught. we wind up with this equals V sub EFF double prime of R naught equals 3 over R cubed times this quantity K R naught minus 3 alpha over R naught minus 2K over R naught cubed plus 12 alpha over R naught to the fifth. Simplifying here, that V sub EFF double prime of R naught equals 3K over R naught cubed minus 9 alpha over R naught to the fifth minus 2K over R naught cubed plus 12 alpha over R naught to the fifth. So that V sub EFF double prime of R naught equals K over R naught cubed plus 3 alpha over R naught to the fifth. So omega sub R squared equals K over M R naught cubed plus 3 alpha over M R naught to the fifth. And equivalently, we would get omega sub R equals the positive square root of K over M R naught cubed plus 3 alpha over M R naught to the fifth. And for stability, we require that omega sub R squared to be greater than 0. For sufficiently small absolute value of alpha, this is stable as long as K R naught squared plus 3 alpha happens to be greater than 0. Okay. Part E now, they want us to determine the orbital angular frequency. So the angular frequency of the circular orbit is W sub theta equals theta dot equals L over M R naught squared. Therefore, omega naught squared equals that L squared over M squared R naught to the fourth. Using L squared over M as K R naught minus 3 alpha over R naught, we get W sub theta squared equals 1 over M R naught to the fourth times the quantity K R naught minus 3 alpha over R naught. So here we get that's W naught squared, W theta, W sub theta squared, my apologies. And why did I call it W? Oh goodness, I have a bad habit with this. Omega, I'm very sorry, omega. Omega sub theta squared equals K over M R naught cubed minus 3 alpha over M R naught to the fifth. So omega sub theta equals the square root of K over M R naught cubed minus 3 alpha over M R naught to the fifth. Okay. So that's letter E. Sorry about calling omega W. I know that's a very bad habit I have at times. Okay. For letter 5, they want us to calculate the leading order apsidal precession per orbit. So leading order apsidal precession are, some people say apsidal. The radial oscillation period is T sub R equals 2 pi over omega sub R. During this time, the angle swept out is delta theta equals omega sub theta T sub R equals 2 pi omega sub theta over omega sub R. For a closed Kepler ellipse, the radial coordinate repeats after an angular advance of exactly 2 pi. Here, delta theta does not equal 2 pi, so the orbit precesses, and we need omega sub theta over omega sub R. Okay, now from here, using the above expressions, omega sub R squared over omega sub theta squared, that's going to equal this, K over M R naught cubed plus 3 alpha over M R naught to the fifth over K over M R naught cubed minus 3 alpha over M R naught to the fifth. Multiplying the numerator and the denominator by M R naught to the fifth, we get the following. Omega sub R squared over omega theta sub theta squared equals K R naught squared plus 3 alpha over K R naught squared minus 3 alpha. And for small alpha, we define epsilon to be equal to 3 alpha over K R naught squared. So then we could conclude there for that portion, the omega sub r squared over omega sub theta squared equals 1 plus epsilon over 1 minus epsilon. And for the absolute value of epsilon is much less than 1. 1 plus epsilon over 1 minus epsilon is that product there, 1 plus epsilon times 1 plus epsilon, 1 plus 2 epsilon. So the omega sub r over omega sub theta is approximately 1 plus epsilon. Therefore, omega sub theta over omega sub r is approximately 1 minus epsilon. So delta theta equals 2 pi omega sub theta over omega sub r is approximately 2 pi times the quantity 1 minus epsilon. Substituting back, delta theta is approximately 2 pi times the quantity 1 minus 3 alpha over k r naught squared. The absolute precession per radial cycle is the difference from 2 pi. So we get that delta, sorry about that poorly drawn delta theta equals the change in theta minus 2 pi. So delta theta is approximately 2 pi times the quantity 1 minus 3 alpha over k r naught squared minus 2 pi. Therefore, that delta theta is approximately negative 6 pi alpha over k r naught squared. To the leading order, one may also replace r naught by the unperturbed Kepler radius, that r sub capital K equals L squared over mk. Then delta theta approximates negative 6 pi alpha over k r sub capital K squared. And this is equal to negative 6 pi m squared k alpha over L to the fourth. Okay, and my apologies if I misread anything here. A lot of variables. Okay, so let's see here. Now we're moving on. I think that was all for letter F. Yep, that's all for letter F, it looks like on that page. Now moving on to letter G. In letter G, for alpha is greater than 0 and alpha is less than 0, determine whether the periapsis advances or regresses. So for letter G, sign of the precession, the result is delta theta is about negative 6 pi alpha over k r naught squared. And we could say here, since k is greater than 0 and r naught squared is greater than 0, the sign is controlled by alpha. If alpha is greater than 0, then delta theta is less than 0, so the periapsis regresses. So that alpha greater than 0, that leads to retrograde precession. If alpha is less than 0, then delta theta is greater than 0, so the periapsis advances. Delta less than 0, that's prograde precession. Okay, so that's practice problem number 2. Thank you very much and have a great day.